Hi everyone, thanks for tuning into the back side of the worksheet for our notes for L'Hopital's rule. We're just going to continue on and finish our 5 examples here on the back and then call it a day on these notes. So here is our first example, example 5. We're going to start like we always do by plugging 0 in. Well, if you take the square root of 1 plus 0 minus 1, you get 0. And here, of course, you get 0. So we have our indeterminate form. So L'Hopital's rule says the limit will be equal to the limit of the derivative of the top over the derivative of the bottom. So let's get going. The derivative of the top. Well, the square root of 1 plus x, I'm actually going to rewrite that as 1 plus x to the 1/2 power so that I can use the chain rule. So using the chain rule, I'd bring the 1/2 down to the front, rewrite my inside, 1 plus x, drop this exponent by 1, so 1/2 minus 2/2 is -1/2, and then multiply by the derivative of the inside here, which again is just 1, minus the derivative of this guy right here is 0, and the derivative of x on the bottom is just 1. So really, when you think about it, I'm just left with really this right here because this part, because minus 0 won't do anything and division by 1 won't do anything. So I'm just going to focus my energies right here. And before I plug 0 in to get my final answer, I'm actually going to rewrite this so it's a little bit nicer. So I'll do the limit as x approaches 0. I'm going to take this back to the bottom. So the 1 here will stay on top. My 2, this is my 1/2, square root of 1 plus x. And when I put my 0 back in here, I have the square root of 1. So my final answer is 1/2. Pretty easy. Looked a little bit messy, but turns out not to be too bad. Let's look at example 6. Put your 0 in. 1 minus the cosine of 0 is 0 over 0, indeterminate. Let's run L'Hopital. Derivative of the top. Well, the derivative of 1 is 0, minus the derivative of cosine x is negative sine x. And on the bottom, I have a derivative of 1 plus 2x. So to clean this up, I might write it as the limit as x approaches 0 of a positive sine x divided by 1 plus 2x. And when I plug 0 back in, the sine of 0 is 0. 1 plus 2 times 0 is 1. And 0 over 1 is no longer indeterminate, it's just 0. Final answer. Okay, let's look at the next one, example 7. The limit as x approaches 0, and here is my function. So if I plug 0 in, I end up getting 1 minus 0 over 2, which is certainly 0. And on the bottom, 0. Always check. You can't use L'Hopital unless when you plug it in here, you're getting this indeterminate form. Okay, so limit as x approaches 0. Here we go. Derivative of the top. Well, I think I'm going to steal something here. Didn't I just take the derivative of this guy right here? I already did him in example 5 right here, and I ended up with this clean answer right there. So I'm going to steal that as 1 over 2 square root of 1 plus x, and then minus the derivative of this 1 is 0, minus the derivative of x over 2. Well, if you think of x over 2 as 1/2 x, then the derivative is simply 1/2. On the bottom, the derivative of x squared is 2x. And so if I replug 0 in, I'm going to have 1/2 minus 1/2, which is 0, over 2 times 0, which is 0. So I'm still stuck in an indeterminate form. So I'm going to go again. I'm going to take the derivative of the top and bottom once more. So now, well, the bottom's easy. The derivative of 2x is just 2. And this guy right here, I mean, the derivative of 0 is still 0. The derivative of 1/2 is 0. So I really need only focus on the derivative right here. So I'm going to rewrite this. Actually, you know what? I'm not going to rewrite it because actually it's rewritten for me right here. This was actually the derivative before I changed it to a cleaner version. So what I'm going to do is I'm going to kind of ignore this 1 because 1/2 times 1 is just 1/2. And I'm just going to run the chain rule again on this. So -1/2 times +1/2 gives me -1/4 times, I'll rewrite 1 plus x. Drop this by 1, so -1/2 minus 2/2 is -3/2. And then times the derivative of the inside, which is just 1. So to clean it up, I'm going to have the limit as x approaches 0. Okay, I'm going to rewrite this as -1 all over 4 times 1 plus x to the +3 over 2, all over 2. Now when I plug my 0 back in, well, 1 plus 0 is 1. 1 raised to the 3/2 is still 1. 1 raised to any power is going to be 1. So this, or you could think of it as the square root of 1 is 1 and 1 to the 3rd is 1. So basically we have -1/4 divided by 2, and that's -1/8. Final answer. And 2 to go. And these are basically the same problem. You see the sine of x over x squared in both. The difference is the first limit here is approaching 0 from the right, and the second is approaching 0 from the left. So let's get into it. First, let's just plug 0 in. The sine of 0 is 0. 0 squared is 0. There's your indeterminate form. Okay, now we take the derivative of the top and bottom. The derivative of sine is cosine x. The derivative of x squared is 2x. Now, if we plug 0 back in here, the cosine of 0 is 1. And if we plug 0 down here for 2x, it would be 0. But it would be just a little more than 0 because the number that we're plugging in is just slightly to the right of 0. And we learned in the first unit we studied that 1 over numbers very, very, very small, but just to the right of 0, approach infinity. So that's going to be my answer for example 8. So what's the catch on 9? Well, there's only one slight difference. You'll start with 0 over 0. You'll have the exact same derivatives, cosine x over 2x. The difference is when you put 0 in here, or even a number just slightly less, your y values from both sides are definitely approaching 1. You can even think of that as, like, think about the graph of cosine of x. Looks like this. There's 1 cycle. Here's 2 cycles. So as you're approaching 0 from both the right and the left, your y values are headed towards 1. So that's why I can put a 1 here and a 1 here. Now with 2 times 0, that would be 0. But since we're just slightly to the left, we'll say slightly to the left and -infinity. Final answer. Okay, so that concludes all of the notes, both sides, on L'Hopital's rule. Thanks for watching and good luck with your work.